We are here to discuss what angle of attack is, why a pilot should fly it, and how angle of attack is flown. This video shows Safe Flight's SCc Indexer Computer displaying the aircraft's angle of attack, mounted on the glare shield. But before we get into the details of it, we're first going to discuss why flying angle of attack is beneficial to the pilot. First, let's look at some accident statistics. The FAA conducted a review of 2,472 general aviation airplane fatal accidents over a 10-year period. In-flight loss of control was identified as the most prevalent cause of these accidents, in which there were 1,259 fatalities. Loss of control, mainly stalls, accounted for approximately 40% of all fatal general aviation accidents. A working group concluded that the use of angle of attack-based systems by the general aviation community would be the most effective method for reducing loss of control accidents in the approach and landing phase of flight. We will be getting into more detail about why they made this claim later on in this presentation. Following the working group's findings, the FAA named AoA as a top life-saving technology, and is on record as stating they want every general aviation airplane to have angle of attack displayed. The FAA also streamlined the approval requirements for angle of attack systems. Supplementing traditional aircraft performance information with angle of attack is beneficial for ensuring aircraft control. So what is AoA? Taking a look at this wing profile, if we superimpose a line through the chord of the wing and lines in the direction of the incoming air, the angle of attack is the angle between the chord line of the wing and the incoming air. In this case, 5 degrees. The direction of the incoming air is dependent on the aircraft's pitch attitude and flight path angle. In level flight, the aircraft's angle of attack is equal to the pitch attitude, adjusted for wing incidence angle. However, when flying the same pitch attitude while descending on a 3-degree glide slope, the AoA increases by the glide path angle. As you can see, the dotted line is the 3-degree glide slope, and you can see that when you're on a glide slope, the incoming air has a different direction. This increases the angle of attack by the angle of the glide slope, changing the 5-degree angle of attack to 8 degrees. Because angle of attack is in reference to the incoming air, an aircraft climbing at 2 degrees and an aircraft on a 3-degree glide slope can actually have the same angle of attack, despite a 5-degree difference in pitch. Here's our first aircraft. It's climbing at a 2-degree climb angle and has a 10-degree pitch attitude, which means its angle of attack is 8 degrees. Our second aircraft is on a 3-degree glide slope and has a 5-degree pitch attitude, so its angle of attack is also 8 degrees. At higher angles of attack, near the wing's maximum lift coefficient, the airflow over the wing becomes disrupted and starts to separate from the wing. Here we're looking at the same profile, but now at a much higher angle of attack. And as you can see, towards the trailing edge of the wing profile, there is the beginning of flow separation. This separation is often, but not always, accompanied by buffeting, as this now turbulent airflow can hit the horizontal stabilizer. This flow separation leads us into our next point, which is what causes aerodynamic stall. At a critical angle of attack, flow separates from the wing surface abruptly, resulting in a drastic loss of lift and an increase in drag, which defines the stall. Under normal flight conditions of relatively low angles of attack, the incoming air flows smoothly over the wing's surface. But at the stall, the incoming airflow separates. It is key to note here that for a given flap position, this critical angle of attack is the point of aerodynamic stall, regardless of gross weight, center of gravity, maneuvering load, bank angle, or turbulence, although the indicated airspeed will vary with each of these factors. Avoiding this critical angle of attack will avoid stall conditions. The following slide explores the relationship between airspeed and angle of attack in more detail. Angle of attack and airspeed both contribute towards the production of lift. If airspeed decreases, the aircraft's angle of attack must increase in order to maintain a constant flight path. The opposite is true. If airspeed increases, to keep the total lift constant, the angle of attack must decrease. So for steady flight, speed is related to angle of attack, with high speed requiring a low angle of attack and low speed requiring a high angle of attack. As the plane slows to an appropriate approach speed, the angle of attack is increased to maintain the flight path. A pilot can avoid stalling the aircraft by flying at speeds that don't require an angle of attack close to the stall angle. This answers the question of why AoA indicators are a life-saving technology. At a glance, real-time angle of attack information allows the pilot to confidently maintain an angle of attack margin above stall by reference to just one flight instrument, and without attempting to adjust airspeed for varying conditions. Having pioneered stall warning in 1946, Safe Flight has developed the SCc to supplement an aircraft stall warning system with real-time angle of attack information. Let's take a closer look at the SCc AoA system. One of the key things to note about the SCc system is that it only has two components. The first of which is the Lift Transducer, which mounts on the leading edge of the wing, and the second of which is the Indexer Computer, which is mounted on the glare shield. On this aircraft, you can see the mounting location of the Lift Transducer. It is important to note that Safe Flight's Lift Transducer is the only angle of attack sensor on the market that measures the wing's leading edge flow, an exact analog of the lift coefficient that angle of attack determines. I'll explain why this is important on the next slide. Let's take a look at how the Lift Transducer actually works. As mentioned earlier, it mounts to the leading edge of the wing. These streamlines represent the incoming air particles, and you might notice that at one position of the wing's leading edge, the airflow divides over the upper and lower wing surfaces. This location is referred to as the stagnation point, the position of maximum air pressure and minimum airflow. By detecting pressure on the Lift Transducer's protruding tab, as the stagnation point changes with angle of attack, the Lift Transducer effectively analyzes the flow field, which determines the angle of attack of the wing. This precise measurement is accurate regardless of weight, center of gravity, maneuvering load factor, power setting, and wind shear and turbulence. This short animation demonstrates the changing wing flow field around the Lift Transducer as the angle of attack increases. Now let's take a look at the SCc Indexer Computer. This is the device that is mounted in front of the pilot on the cockpit glare shield, in a location which provides AoA information without obstructing the pilot's view through the windshield of the runway during takeoff or landing approach. The SCc also has a low airspeed awareness function that alerts the pilot to impending stall. In combination with the blinking amber LEDs associated with low speed awareness, the SCc has a Geiger counter-like audio warning as the AoA increases into the high AoA region approaching stall. This feature is also mutable, which is useful for low-speed flight training. The SCc also has a pilot-selectable target AoA reference marker to allow the pilot to establish AoA targets for specific operations, such as long-range cruise, maximum endurance, and short-field takeoff and landing. The device is also optimized for sunlight and nighttime viewing with the provision of a dimming feature. Let's take a closer look at the system operation. Angle of attack information is provided by the sequential display of LED lights on the Indexer computer. In addition, there is also a pilot set reference marker that can be moved up and down to target certain angles of attack. The top button moves the reference marker up, while the bottom button moves the reference marker down. These top and bottom buttons also serve to mute and dim, respectively. The entire device sits atop a ball mount for optimized viewing by the pilot. So how does one actually read the SCc? LEDs on the Indexer computer illuminate, graphically representing the wing's angle of attack. The on-speed condition, shown now by the SCc, is calibrated to the angle of attack flown for a normal approach, according to the POH. Lights displayed below the on-speed configuration indicate a lower angle of attack. The single dot seen now represents what the pilot would see while flying at a nominal high-speed cruise. During landing approach, a pilot would reduce power setting, slowing down to maintain targeted approach AoA, with the corresponding LED pattern. LEDs displayed above the on-speed configuration indicate a higher angle of attack. Should the LEDs illuminate towards the top of the Indexer computer, both the flashing color and the Geiger counter-like audio would warn of impending stall conditions. The pilot should pitch down and increase power setting to speed up and regain the landing approach target AoA. Now we are going to take a little bit of time to talk about the traditional airspeed indicator. The edges of the white and green arcs on your airspeed indicator are the full flap and zero flap stall speeds respectively. These speeds are for 1G flight at max takeoff weight, a typical mid-range center of gravity, with power set to idle. As such, these airspeed indicator markings do not provide any corrections for weight, center of gravity, maneuvering load factor, power setting, and wind shear and turbulence. The POH does include some information on stall speed adjustments, but these are not reflected on the airspeed indicator. Let's see how stall speed is affected by several factors, using the sample stall speed chart from a POH. To read this chart, one must first locate the current aircraft gross weight, which in this case is 2150 pounds. From this reference point, they would move up to the flap setting, which in this case is 40 degrees. Reading across to the 0 degree bank angle, and then up to the current bank angle, which is 20 degrees. From here, they would read across to the y-axis to find the calculated stall speed, which ends up being 44 knots. This would be very difficult to do while maneuvering the aircraft, and is still limited by the factors it doesn't account for, like center of gravity, power setting, gusts, and turbulence. The next slide explores the reasons behind the stall speed adjustments for bank angle and how they relate to angle of attack. Let's look at the aerodynamics of a constant speed bank. First, it is key to note that the upwards lift must balance the downwards force of weight, no matter the bank angle, to maintain altitude. This blue dot on the graph represents the plane, currently at a 0 degree bank at roughly 62 knots. This red line is the stall speed, also shown by the red arrow next to the ASI, which will move as we bank. There is currently a 19 knot margin above stall. This green line is the line of constant speed we will be flying along, also shown by the green arrow next to the ASI. As the plane banks to a 45 degree bank angle, the margin above stall is reduced to 10 knots, because the angle of attack had to increase, as shown on the SCc, to generate more total lift, so the upwards component remained constant. Thus, to maintain altitude, the total lift had to increase by 41%, while the stall speed increased by 19%. This effect is furthered as the bank angle continues to increase to 60 degrees. To maintain altitude at 60 degrees, the total lift has to increase by 100%, which means the stall speed increases by 41%, which in this case results in a stall. Now let's consider a different scenario, a constant angle of attack bank. In this case, instead of flying along a line of constant speed and increasing angle of attack to generate more lift, we will fly along a line of constant angle of attack and increase speed to generate lift. As the plane banks, the pilot adds power to increase speed, which allows the wing's angle of attack to remain the same, as shown on the SCc. Increasing airspeed to fly this constant angle of attack automatically maintains a safe margin above stall. By being able to observe one's angle of attack, the SCc enables such maneuvers. Now that we've discussed the theory behind flying angle of attack, the following slides cover the general usage of the SCc and adjustable reference marker. For normal takeoff, the SCc should display the 5 lights in the plus configuration for on speed. Setting the reference marker higher, in accordance with POH reference shortfield speeds, and aiming for that slightly higher angle of attack is optimal for a shortfield takeoff, as it allows for the best angle of climb. For an approach, the on-speed configuration should be displayed. If one is flying too fast, the SCc will display lights below the on-speed configuration, as the higher speed necessitates a lower angle of attack. Conversely, if one is flying too slowly for an approach, there will be an indication above the reference marker for on-speed because of the higher angle of attack. For a shortfield approach, setting the reference marker higher than that for the normal on-speed configuration, in accordance with POH reference shortfield approach speeds, and targeting this angle of attack, allows the pilot to fly the slower speeds required for a minimum distance landing. Let's look at the benefits of the SCc applied to the base to final turn. According to general aviation accident data, base to final is one of the most dangerous phases of flight. A pilot must process and assess rapidly changing conditions, all while maintaining control of the aircraft. We will go through the following scenario, first on a flight without the benefit of Safe Flight SCc. Flying the downwind leg of the approach, a crosswind, which is not compensated for, pushes the aircraft closer to the runway than planned. The pilot now turns onto base, still encountering the crosswind, with the aircraft off track. The pilot realizes that the crosswind has displaced the aircraft off the proper track and will overshoot the runway centerline. In an attempt to correct, the pilot steepens the bank angle and adds rudder to increase the rate of turn, and adds nose-up pitch to check the rate of descent. This maneuver causes a rapidly increasing angle of attack, which in turning flight can result in a spin entry. At low altitudes of landing approach, recovery from this condition may not be feasible. Notice that the ASI gave no indication of the impending stall. Let's look at the same situation, but now this time, the aircraft has an SCc installed. Flying the downwind leg of the approach, just like before, a crosswind pushes the aircraft towards the runway. Notice that while the pilot slowed down, the AoA increased towards the display of the correct POH target speed, adjusted for the aircraft's actual gross weight and flap position. Now the pilot turns onto base with the crosswind, as in the previous example. The pilot realizes the crosswind has displaced the aircraft off the proper track and will overshoot. To try and correct, the pilot steepens the bank angle and adds rudder to increase the rate of turn, and adds nose pitch up to check the rate of descent. Notice that the SCc is now displaying a warning. Recognizing the dangerously high angle of attack resulting from the uncoordinated turn, the pilot adds power and performs a go-around. Let's go over the key takeaways from this presentation. The FAA has determined that stalling is a major cause of general aviation accidents and fatalities. Airspeed indicators do not account for many factors that significantly impact stall, such as weight, center of gravity, maneuvering load factor, power setting, and wind shear and turbulence. Recognizing that the display of AoA will allow pilots to more effectively maintain a margin above stall conditions, the FAA is encouraging their development and implementation. Safe Flight solution, the SCc, provides clear, understandable, and pilot-adjustable sensing and display of angle of attack. For more information, visit www.safeflight.com.